Okay, let's get started. So today is the last lecture before Thanksgiving, so usually late attendance. So are there any questions, first of all, about course logistics or course material in general? Yes.
Is homework 6 the last homework, or is there another one?
There's gonna be a really short homework posted today or tomorrow. It'll, yeah, homework 7. It'll be about half the size of typical homework. Okay. Yeah. So it's probably going to have one MATLAB thing where you do simulate image contrast and another one where you sort of go through and check off some things. So it should be relatively, the scope of it should be about half what you're used to. Okay. Any other questions? Okay. So with that, I guess the other thing is that some groups did approach me about, like, for example, about trying to get more feedback on their project 1 scoring, if because they wanted to sort of see what they could improve for project 2. So if you, the notes we have are very sort of messy. So, but if you do want to have a summary of it, just send me an email. I've already done that for one group, and what I'll do is I'll sort of do a sanitized summary version for you to give you feedback. But the general feedback is sort of what we've been talking about, and then that's specified in the project 2 requirements. I went back and emphasized a little bit what Professor McVeigh and I will be looking for, which is typically make sure you cover, you relate your presentation to the course material, don't get too off track. And so I think I gave feedback to a few groups on that. And then also, if there is no computational, if there's nothing done beyond just sort of repeating what's in the literature, then it is hard to get really good points on difficulty parts. So we're not expecting anything world shattering, but we do expect something there. And you've sort of seen the range of sort of projects from project 1. And so, that spanned the whole range from full points for difficulty for very little points for difficulty in terms of how we scored that. So I think that's probably the most useful feedback. But if you do feel like you want a summary of your project 1 comments, then just send me an email. All right. Any questions on that? Okay, so let's get started. Today we're going to focus mostly on starting image contrast. And so we're going to first talk about the most common types of image contrast. Then we're going to hopefully talk about functional MRI. And then if we have time, get to diffusion imaging. So just to remind you where we were last time, we spent quite a bit of time talking about T1 and T2 and how these depended on molecular tumbling rate. And I think there was a question on that in the pre-lecture quiz. I think everyone got that right, so that's good. And the key thing that we're going to take advantage of today is the fact that different tissues have different T1s and T2s. Okay. And therefore, we should be able to take advantage of this to differentiate different tissues and basically create different types of contrast. So we'll talk a little bit about how we do that. And that is a major part of MRI in terms of when radiologists are prescribing different protocols, they have flexibility to choose different parameters. And so they will want to pick the parameters that emphasize the contrast that they care about the most. We also talked a little bit about things that are due to static inhomogeneities. And so we saw these pictures here where anything that causes inhomogeneities in the field will cause dephasing and therefore signal dropout. Okay, and we saw these examples from last time. And the way we sort of describe those things is with this T2 prime term. Okay, so and then the effective time constant is then T2 star. So we have T2, which is due to random motion of spins, and then we have T2 prime, which is due to the static dephasing. Okay, and as we talked about last time, we can also write it as an inverse R2 star, and we'll see this later in fMRI, equals R2 plus R2 prime. So I think the only one question where there was maybe some confusion was when we talk about a rate, that's the R2 prime, the R2 star, okay? And so that rate, the more inhomogeneities there are, that rate will tend to increase, right? Because things are going to dephase faster. And then, but conversely, that means that 1 over that T2 star, 1 over our 2 stars, T2 star will be shorter. Okay, so there's more signal dropouts. So just to remind you, R2 star equals 1 over T2 star and vice versa. Right? So it is important to always check and see if you're looking at either a rate or a time constant. So we talked about gradient echo sequences. And so when we talk about image contrast, it'll be important to see if we're talking about a gradient echo sequence. And a gradient echo, remember, it's defined as simply the rephasing of the spins that occurs due to the gradients. Therefore, it's a gradient echo. And it occurs where we cross center of K space, here Kx equals 0. And therefore, this echo forms here. Okay. But it's downweighted from what we expect to do because of this T2 star weighting. So if without the T2 star relaxation, the signal would be up here. With the relaxation, we're losing signal as signal is dephasing. Right? So the time at which we acquire it is called echo time, TE. Okay, so this is going to be a very important parameter. So one of the options we're going to have to deal with is TE, echo time. And you notice if we went out too far in echo time here, the signal, we'd have no signal. Okay, so we have to acquire the data within an echo time that's on the order of T2 star or shorter. Okay, if we go out to, for example, 3 or 4 T2 stars, we have no signal left. And therefore your image will be totally black. And that's not usually very useful. Now, the other sequence we talked about is called the spin echo pulse sequence, which we'll also be talking about later in this course. Now the echo time is a little different, okay? Because now, in addition to these gradients, we have this 180-degree refocusing pulse, okay? And this is used to refocus those static inhomogeneities such that we wait some amount tau, so we let the spins dephase, we flip the spins with the 180, and then we wait a certain additional amount tau for them to get back into sync again. And then we acquire the echo at that time. And you notice here, we've gone from basically, the weighting here is T2, no longer T2 star weighting, okay? So there'll still be some weighting because of T2, and then the weighting around it is going to be a T2 prime weighting, all right? So now, in general, if compared to T2 star, this should be a little bigger. So probably in next year's slides, I should make this a little bigger signal because we will have recovered a lot of the signal because we've gotten rid of the T2 star weighting. And this is an example of this where we saw this last time, where in areas where there was a lot of signal dropout with a gradient echo image, that's taken care of with a spin echo image. Okay, so clearly a lot, essentially no signal dropouts here, quite a lot of signal dropouts in this image. Okay, so to wrap everything together, when we talk about image contrast, the main things we're going to have to consider are T1 recovery. So this is the recovery of the longitudinal relaxation, longitudinal magnetization back to M sub 0. And then we'll also have to consider either T2 star decay or T2 decay. So T2 decay is if we have a spin echo image. T2 star decay is when we have a gradient echo image. Okay. Now you might ask, why do we use gradient echo if it has much faster decay? Why don't we always use spin echo? Because it has this nice, we recover some of the signal. It turns out that sometimes this T2 star decay is very useful. Okay, and so in fMRI, you'll see we actually make advantage of this T2 star decay. It also is because those 180-degree pulses, to put those in, that's injecting energy into the sequence. You're also having to wait more time. So certain times when you want to go really fast, you might choose to do gradient echo and just set things up such that if the T is short enough, that you're not going to get that dephasing. Okay, so gradient echo is still an option if you can acquire relatively high up on this curve, and you do that and just go super fast. And then you don't have to stick in those 180-degree pulses, and it can save you time, and also it's less RF energy that's deposited into your subject. Okay, so now we're going to, based on that background, we're going to transition into image contrast. So we've talked about, we expect that different tissues will have different relaxation rates. T1, T2, and T2 star. In addition, there's going to have different density of protons, right? Certain areas are going to have more protons than others. Like cerebral spinal fluid, the water that bathes your brain, will have a lot of protons per unit volume. Whereas something like your lungs, right, where there's a lot of air, there's not going to be that as many hydrogen protons per unit volume. Okay. So the first thing we're going to look at for manipulating contrast is adjusting these two parameters, TE echo time and TR repetition time. Okay, so those are the two things, the two primary things we're going to manipulate. What we want to see is how, by just using those two parameters, can we get something to be either T1 weighted, T2 weighted, or proton density weighted, right? So the basic sequence we're going to use, we'll have both gradient echo or spin echo, and they're what's called saturation recovery sequences. Okay. That's because we start off the sequence with a 90-degree pulse, okay, that flips the magnetization onto the transverse plane. So we start off the longitudinal component at 0. So anytime you have a sequence that sets the m sub equal to 0, that's called saturation. You saturated the spins, okay? And then we basically repeat this process over and over again, and the interval between excitations is TR, which is the repetition time. And then TE here is the echo time, where the echo is defined as where you cross the center of K-space. Okay. So we have that, then we can say an image that we acquire at a place, at a location X and Y, part of the strength of that signal is the density, rho xy. That's how many spins you have there. Okay. The other thing that's going to determine how much signal you have is this longitudinal relaxation. Okay. The longitudinal relaxation starts off here at 0 and then recovers to some value. And that's the amount it recovers is how much magnetization you have to tip into the transverse plane. So there's this longitudinal relaxation term. And then there's this T2 star decay term. Okay. So this is sort of like, depends on how much money you have in the bank. However much money you have in the bank is that's how much you can use. And this is sort of how fast the money is going away. Okay. So if you don't have much money in the bank, there's not going to be much signal. And if you're spending the money very quickly and you wait too long, there's not going to be much signal. Right? So that's sort of, you can think of, you have this bank of spins that you can use. We can also consider a gradient echo sequence. Now the only difference is we have a 90-degree pulse and a 180-degree pulse. Here we require echo time, where the spins have rephased. And the expression is the same as above, except now T2 star is replaced by T2. Okay, simply because we've rephased the spins so that now we only have T2 weighting. So these are the expressions that we want to look at, and now we want to just sort of say, well, if I want something proton density weighted, ideally I'd like to get rid of these terms, right? And if I want something T2 star weighted, ideally I'd like to get rid of this term. Okay. There's really no way I can get rid of this term very easily because that's just the density of spins. But I can play around with things to get rid of these two terms. All right. And so that's the trick we play with T1 and T2 weighted and proton density weighted images. Okay. So it's actually pretty straightforward. If we want a T1 weighted scan, we want to make this term go away, right? And the way to do that is just make this TE as close to 0 as we can, right? Because then it just becomes 1, right? And if we do that, then we end up with something that has both proton density and T1 weighted. Okay, so now this is more sensitive to the T1s of tissue. So the principle behind T1 weighted contrast, this is from the book, is if I have a short T1, right, and I start off at some magnetization, then by the time I'm ready and the magnetization recovers relatively quickly, then I have a lot more magnetization to tip over on my next excitation. Whereas if I have a very long T1, it doesn't grow back as fast. And so I have less magnetization to tip over. Okay. So this will tend to make long T1 tissues darker and short T1 tissues brighter. Right. So that's the basic T1 contrast for this type of image. So let's look at an example of this. So this is a plot where I'm just plotting the longitudinal recovery as a function of TR for a T1 that's shorter at 800 milliseconds and a longer T1 of 1200 milliseconds. Okay? And you can sort of see there that they're recovering at different rates. And then I can take the difference of these two, and this is the difference image here, the difference signal. And you can sort of see that that difference is maximized around T1 of TR of about 1000. Okay. So that's a pretty good rule of thumb is if I have two tissues that with different T1s, the difference between those two will be maximized when the TR here, so max, sort of TR sort of with the max signal, max difference is around T1 for the first tissue plus T1 for the second tissue, sort of the average of those two. Okay. So that's just a rule of thumb where if you really had to make a decision as to, okay, I have these two tissues and I want to pick a TR that maximizes the contrast or the difference, then a pretty good first estimate before you run lots of simulations is just to take the average of those two T1s, right? Okay, so here are some images of T1, and you can sort of, one thing we saw that is fat, for example, has very short T1s. So we did T1 weighted imaging, then you end up with images that have a lot of fat in them. And so, for example, in this person, the corpus callosum is sort of like the major superhighway that connects the two halves of your brain. And it shouldn't have this much fat in it, but in this person, there's a lot of fat in the corpus callosum. Okay, so he has the, what is it called? Lipoma of the corpus callosum. So sometimes for certain diseases, for example, like liver disease is one where there's you probably heard like fatty liver disease, or really care about how much fat there is, and so it's somewhat useful as a first line of imaging to just sort of see how much fat is there, and that will appear bright in these T1 weighted images, and then if necessary, then there are more quantitative approaches you can do to say, well, what's the percentage of fat, or you can get more quantitative. But as a very first pass, it's sometimes useful just to sort of see what the overall fat presence is. Okay, the next thing we want to talk about is T2 weighted scans. And so here, we just want to make TR very long compared to T1, okay? Because if we make TR very long, then all tissues will recover back to M0, right? So there's no difference in T1s, right? So for example, if you look at this, right, if I make TR very long, they go back to the same M0. And so for T2 weighted scans, if I do that, then there's no dependence on T1 anymore. And so I just have proton density weighted, and then I have, in this case, a T2 weighting, okay? Assuming I'm done a spin echo image here. So let's consider two scans once again, where you can see that this one is decaying with 80 millisecond T2. This one's decaying with 120 millisecond T2. And this is the difference between the two as a function of echo time here now. Okay. And here, this maximum here, that's about 100, right? Which occurs at, the average of 120 plus 80 over 2. Okay. So once again, a good rule of thumb is if you have two tissues with different T2s, okay, if you want to find the echo time that maximizes the contrast, then once again, you can sort of take the average of those two. That's a reasonable guess. So things with really long T2, as you may remember, are cerebral spinal fluid has a very long T2. Okay. So when all other tissues have died away, there's still going to be a lot of signal from T2 because the signal there doesn't die away very quickly. And so that's why, for example, in a normal T2 weighted scan, all the bright spots here are these are the ventricles in your brain, these sort of little volumes in the brain that carry cerebral spinal fluid. which bathes your brain and removes sort of toxins away from your brain. And there's actually a very, actually current state of the art in science is actually looking at what's called the glymphatic system, which is sort of how does CSF help drain toxins from the brain, and whether that's, for example, impaired in certain diseases like Alzheimer's, or for example, maybe especially as people get older, people don't sleep as well. And so the ability of the brain to get rid of toxins may be impaired. And so that's something that actually is a current topic of research that people are looking at. And one of the ways they do it is by using MRI to look at, how much CSF is in the brain, and also you can use it to actually measure how the CSF is moving in the brain. Another application is anytime you have damage, and here there's a cyst. So typically around any lesion or any tumor, there will tend to be a lot of fluid that develops because the tissue is not normal, and so it will tend to be also abnormal in how much cerebrospinal fluid there is. And so in this case, obviously, it's a clear, there's clearly something wrong with this. You don't need an MD degree to diagnose that there might be something wrong. Okay. And the last thing we want to talk about is proton density weighted images. And so here you're saying, well, I'd like to get away from things that are sensitive to T1 and T2. I just want to see how many spins there are per unit volume. And therefore, I want something that's related to proton density. So therefore, we want a very long T1, so everything is recovered. And we want a very short TE, so nothing has decayed away, right? So if we do that, then these T1 and T2 terms are no longer there. And we have something that's primarily related to proton density. So this is an example here where it's a proton density weighted image where they're looking at a patient with, I believe, multiple sclerosis, and seeing that there are sort of diffuse changes in the white matter density. So all this black stuff here is white matter, okay, and these are the ventricles, and so you're sort of seeing here in a normal person, this should be dark, and this is indicating for whatever reason there's maybe some maybe more fluid here or something or some change that's causing more protons to appear here in the wiring of this person's brain. So multiple sclerosis is one of those diseases where there's sort of degradation of the axons in your brain. The myelin around your brain tends to decay. And so as that damage is occurring, you would expect to see changes in the proton density. Okay, so let's do an in-class exercise. Unfortunately, I'm having trouble setting up the poll everywhere. So we're gonna just sort of, the attendance is relatively light today. So I think what I'd like to do is still have you think through this, and we're just gonna sort of talk through this together, and it's a small group so we can sort of be a little more interactive. But here's the thing I want you to think about. And then what you're going to do on the homework is essentially create images that look like this. So you're going to create synthetic T1, T2, and density weighted images. So at least you sort of see what that looks like. But let me just walk you through what you're seeing here. This is the same brain, okay, taken in the same scan session, all right? And all we've done here is manipulated the TR and the TE. Or you could get these, I don't know exactly how these are obtained, but you could get similar looking images by just manipulating the TR and the TE of the different, for each scan. So let's assume that each of these is obtained with a different TR and TE, okay? And this is what you know about the tissue. You know that the proton density, CSF, we'll pick that as a reference, has 1, so it has the most density, and then with respect to that, gray and white matter has less density. And just to tell you what's gray and white matter, the dark parts here are CSF, okay, those are your ventricles. This part here that's sort of white is the white matter, and that's the wiring of your brain. And then if you notice the gray parts around here, we zoom in here, sort of notice how there's sort of somewhat gray parts here out here. That's all your neurons. That's actually what's doing the computations. It's a little more obvious here, this density weighted image. So for example, this all here is white matter, and this is your gray matter. That's your brain. Okay, this is the wiring of your brain. These are the neurons in your brain. And then here is the cerebrospinal fluid, but there is some blood in there as well. Okay. But to first order, you can sort of think about things as CSF, gray, and white matter. The T1 of those different tissues is listed here. Okay. And the T2 is listed here. Okay. So I'd like you to sort of take a couple of minutes and just think about what values of TR and TE we could use to achieve either a T1 weighted image, density weighted image, or a T2 weighted image. Okay. So I'll ask people in person in a few minutes, and then online, if you just want to post your answers to chat or chime in, you can do that as well. Okay. So go ahead and take a look at that, and if you have any questions about what we're asking for, just feel free to ask. I never turned on the intercom, but am I loud enough, or do you want the intercom? Do you want the speaker? You can hear fine. Okay. Okay, so let's discuss, and so let's consider the T1 weighted image first. So should I use, like, what should I use for the echo time? Should I use a long echo time or a short echo time for T1 weighted image?
Short.
Short, right. So why should I use a short echo time? Anyone? So for T1 weighted image, so for T1, I want to use a short echo time, right? About 0, let's say. Why do I want to use a short echo time? Yeah, because e to the 0 is just 1, right? So that's great. Okay, what about TR? What should TR be? given that the T1s are about 4,000, 1350, and 850, what'd be a reasonable value of T1, TR? About 2,000? Okay, let's think about that. So this is a little tricky, right? Because I have 3 tissues I want to have contrast, right? So if I take the average of those 3, maybe I'm not going to have so much contrast between gray and white. Okay. And so it turns out that for this one, it's a little better to take the average of these 2, gray and white, right? Because if I pick anything here, this one's so far out, it's still going to be dark no matter what I pick. Okay, so for this one, I probably want to pick TR closer to about what's the about 1100 maybe. What's the average of these 2 numbers? Let's see, 0, 1 should be 2200, right? So 1100, right? So in that case, if I'm just sort of doing a back of the order computation, I'd probably want to pick TR closer to about 1100, because that will give me contrast between the gray and white. We can sort of see there is some contrast. And then this is so far out, it's going to be dark. It's still going to be dark. Okay. Great. So that's T1. How about density weighted? That's a little easier. So what should TE be for density weighted? Do I want a big TE or a small TE for density weighted? Also small, right? Because we want that term to go. Now here's a sort of a tricky question. How big do I want to make TR? We want to make TR as big as possible, right? And we want to make TR big so we don't get any T1 relaxation. But the question is, how big do we want to make it, right? Because the bigger we make TR, the longer the scan's going to take. So clearly we don't want to make TR like an hour, right? That would be ridiculous. So what would be a reasonable value for TR here? How many T1s do we want to wait?
And it is still 3,000-4,000 milliseconds?
Yeah, so 4,000 milliseconds would be about the T1 of CSF, right? So we'd still have some T1 waiting of CSF. So typically for exponential recovery, you want to go up to about 3 to 5 time constants, right? So we really wanted to be super sure. We'd have 5 times 4,000, which is 20 seconds. But that's a little overdoing it, because even by 3 time constants, you're already like 98 or 99. You're very close, right? So 3 time constants would probably be sufficient. So if I was doing this, I'd probably make TR equal to 12,000. Okay, because otherwise, if you move it out to 20,000 milliseconds, you're waiting much longer, but you're really not getting much difference. Okay, great. And then finally, what do we want to make TR for T2 weighted image? That should also be about 12,000, right? The same argument we made for the proton density. And what about echo time? Now we have to think a little harder. What should echo time be? So we want that echo time. If it's short, there's no contrast, right? And if it's too long, there's no signal. So where do we want it? So given that these are the T2s of the tissues, where should we put that echo time?
In between the 110 and 80.
Yep, that would be the right choice. About 95, right?
Yeah.
Right, because this one has such a long T2 that doesn't really matter where we pick it. So we might as well get contrast between these 2 tissues, and this one is still going to be super bright because it's got such a long T2. Okay, so that's great. I think it seems like people are getting the hang of that. Any questions on this? If you understand this is really the basis of the basic sort of concepts you need to know for this type of saturation recovery contrast.
Professor, quick question. So the slice of the brain here, is it a same slice for all 3, or it was captured differently by adjusting T1, T2 for each category?
It is the same physical slice.
Okay.
And the only thing that's changed is the person at the scanner has changed.
Change the T1, T2. Okay, I see. Thank you.
Now, I don't know exactly how these were acquired, so they may have changed other things, but you'll see on your homework, just by changing TR and TE, you can create different types of images, okay? Okay, so now I'm just going to give you sort of some general information about sequences you will see in practice, simply because it's, although we cover the basics here, what's used in practice differs from it a little bit. So previously we've talked about saturation recovery, in which case this is 90-degree flip. Okay, but that means that on every excitation you're setting the m sub z equal to 0. Okay, so you're basically now you have to wait t1 for the magnetization to recover from 0, right? So as I said before, or in a previous lecture, analogy for this is if you have like an old-fashioned toilet where the water has to build up, right, for you to flush it. Saturation recovery is like you flush the toilet completely, right? So now there's no magnetization, there's no water left, but you have a very strong flush. But now you have to wait for the toilet to go back to its original height in water. One of the insights that was made probably 30 years ago, and I think made the inventor very rich, was the inventor of what's called the flash sequence. And his insight was, actually, if I want to go super fast, I don't want to use 90-degree flip angle because then I'm waiting around a lot. I should be able to use like a smaller flip angle, 10, 20, 30 degrees, okay? Because even, say, a 30-degree flip angle, if I think about sine of 30 degrees, that's a half. So I get half the magnetization that I need, and yet I'm still left with like cosine of 30, which is like 0.87. I'm still left with a lot of magnetization in the longitudinal axis. So therefore, it's sort of like doing a very, like a very light flush of the toilet, enough to do what it needs to do, but then you don't have to wait so long for it to refresh. And that's exactly the idea behind the flash sequence. And so this is the bread and butter of a lot of very fast sequences. Okay. So for example, when you're in an MR scanner, one of the first scans that's done is what's called a localizer scan, where they actually, you put the person in, let's say you want to image their brain, you're not really sure, you need to be able to prescribe your slices. So the first scan is they'll just do very quick scans of 3 scans this way, 3 scans this way, 3 scans this way, okay, in the different planes. And so you'll get a bunch of scans very quickly, done typically in like in 10 seconds, where you can see, okay, this is where the brain is, and now you can do what's called prescribe the areas you want to look at. All the subsequent scans will be prescribed on that localizer scan. So you don't want that localizer scan to take very long. And so that's why most localizer scans you see will use this flash sequence. So it has this expression like this, which we're not going to go through. And the signal intensity, it turns out you can maximize the signal intensity given a TR and a T1. If you pick your flip angle correctly, you can actually maximize the signal. Okay. And this is an example here where, for example, you can sort of see here for this is a T1 of 1,000 milliseconds. Okay, so typically for saturation recovery, we know the TR has to be on the order of that, right? So like a second or more to get enough recovery of the signal. But notice here, if I go down to TR 500 milliseconds and I pick my flip angle right, I can get half the magnetization I want, and I can go 2 or 3 times as fast as I could. And if I'm willing to take even a bigger hit, let's say go down to a TR with 100 milliseconds here and pick the right value, I can get about 25%, let's say, of my maximum intensity. But the gain is I'm going 10 to 20 times faster now. Okay. So that's a trade-off that we will sometimes make in MR. We have enough signal to burn, we're going to use that to go faster. The other type of sequence that's commonly used is what's called inversion recovery sequence, and this is what it looks like. So you've seen this one before. This is just the spin echo part, okay? The 90, 180, and the acquisition. Now here, what we do is before we even excite any spins, we actually invert them first. And then we wait for them to recover. And so that changes our expression to this, okay? And this has a very interesting property. Because this was set to -1 initially, it's got to go through 0 at some point. And in fact, the intensity of this curve will be 0 when we set this inversion time equal to this value where we have both the T1s and the TRs in that expression. Okay. Oops. With my mouse. Okay, it's back. So that's shown here where, for example, I have different types of tissue and they go through inversion recovery, and at some point they're going to go through 0. Okay, and different tissues will go through 0 at different points. So depending on where I collect the data, I can tune what I'm nulling out. So for example, you notice here CSF is very bright, but here it's very dark. Okay, and so you sort of notice what's dark is varying as I go across these images because I'm nulling out different tissues based on their T1. For example, here stir is often used to null out fat, and so here you notice if I acquire here, fat will be close to 0, where muscle and fluid are negative, but that's okay because if it's negative and I flip it 90 degrees, it still flip back onto the transverse plane. Okay. Here I time it to null out fluid, okay, and I can even do things like null out things like blood. So for example, here I've nulled out the fluid. I've made this look very dark, saying I want to look at my brain, but I don't care about all the fluid bathing the brain. So give me an image where I don't have to see that fluid. Okay. Similarly, when I'm imaging the heart, I may not want to see all the blood swirling in the brain. I want to be able to see the heart walls better. And so in this case is what's called a black blood image. Okay. Just basically make that black. I can take this even further, and by applying a bunch of 180-degree pulses, I can null out lots of different tissues. And so, for example, here, I've nulled out everything except for blood that's flowing. Right? So there's a lot of tricks that people have come up with over the years applying these sorts of methods. Okay. So we're not going to go into too much detail, but I just want to show you that we've covered some of the basics of the saturation recovery sequence, but in practice, there's a lot of variations that are used and have been developed over the years. So before we move on from basic image contrast, are there any questions? Okay, so we're going to switch gears here and talk a little bit about fMRI, which stands for functional MRI. And so far, sort of the implicit assumption is we want to study something like brain anatomy. Yes, question.
Would it be useful to like having contrast between the PCI scan? Instead of just like a proton,
yeah, right. So that's a good question. So that's called like multinuclear imaging. So we can, for example, there's like phosphorus imaging, which can be useful for looking at muscles. There's sodium imaging, which can be useful for looking at just overall physiological state because of all the sodium pumps and things like that. There's oxygen O17 imaging, which you can use to like image oxygen. So it is possible, but it's not used that frequently simply because the abundance of those is very low, so the sensitivity is very low. So it's very hard to get. Typically, images are very low resolution. And so there are people working on that still, but in terms of clinical practice, I would say it's not really that prevalent. It's still more of a research tool even today. Now you can do proton spectroscopy, which is basically, you know, the hydrogen protons, there's a lot of hydrogen in different atoms and molecules, right? And each, depending on whether you're in one molecule or another, the hydrogen protons will have different resonant frequencies. So around the main resonance of water, you'll see other things like lactate or choline, and those are still hydrogen protons, but because they're within some molecule, they have a different resonant frequency. So you can do what's called spectroscopy or chemical shift imaging, but there again, you're dealing with very low levels of metabolites. So there's interest in it because obviously, you know, if you can really do spectroscopy very well, then you can start looking at chemical exchange and map out different chemical pathways. But in practice, it's still difficult to do. So there is interest in it, but it's not as common as sort of the standard proton imaging. But that's a great question. Okay, getting back to fMRI. Yeah, the idea behind fMRI is we want not only to study what things look like, but we want to see what they're doing. And in this case, what is the brain doing? Okay. So a typical setup is pretty much like an MRI exam where you put the person in the scanner. The only difference is a lot of times you'll ask them to do something. So you can have a screen that they're looking at. They could be playing a video game, or they could be gambling, or you could be trying to scare them with scary faces. And then typically there'll be some way for them to respond. Okay? Even very sophisticated ones might even put them into a virtual reality environment where they're using VR goggles and they feel like they're navigating through something. And you're just trying to see what the brain is doing as it's doing different tasks. So fMRI is relatively recent. The first studies were done in the early 1990s. Seiji Ogawa was sort of credited with sort of coming up with the idea for this. The basic phenomenon, one of the first experiments they did was very simple. They just showed person either they were looking at light or it was dark. Okay, and so this was sort of, and they found out if they looked at this part of the brain here, and so with fMRI we typically look at, you sit on one part of the brain and you're sort of seeing what its activity is. And what they noticed was that the fMRI signal went up as the person was looking at light, and then down, and then up and down again. Okay. And if they went to another part of the brain that is not really related to vision, then they didn't really find much activity. So this is sort of the basic of how fMRI works. The other interesting thing is that they found out if they used a short echo time, they didn't really get much signal. They actually had to go out to a longer echo time to sort of start getting some signal. So this is one of those clues where this must be related to some sort of relaxation, right? Because it's either T2 or T2 star relaxation, because if echo time is very short, then that e to the minus TE over T2 or T2 star is not really going to vary as T2 or T2 star varies. So you've got to go out to a longer echo time to get this signal. So fMRI is super popular since the birth of fMRI. You can sort of see there's like 10,000 papers a year. It's probably more by now. This was done in 2014. Okay, so very, very popular tool for research. Not as widely used clinically, but for research, it is one of the primary methods we have now for studying the brain. The main trade-off we make in fMRI is we've talked a lot about sort of setting up our acquisition to get very nice resolution. And so for a typical high resolution scan of the brain, you might want a voxel volume of like 1 millimeter isotropic. And typically you'll spend about 6 minutes to acquire that very nice anatomical picture of the brain. But for studying brain function, 6 minutes is sort of a very long time scale, right? I mean, neurons fire in tens of milliseconds. Even if you subjectively watch your brain and what it's doing, things are changing pretty much every second, right? I mean, your thoughts come in and out, your brain's controlling your breathing, your motion. So you want to be at least on the second time scale, right? Minute time scale, just so much would happen, right? 6 minutes ago, I don't even remember what we were doing, right? So therefore, we've got to get down into the minute time scale. And here, this image is much lower resolution. So this is, instead of 1 millimeter cubic, this is 45 millimeter cubed. So that would be about what? Let's see, 3 times 3, 27. So between 3.5 millimeter isotropic, say. But the thing is, this slice could be acquired in 60 milliseconds or less, very quickly. Okay, so we can acquire a slice of images very quickly, and then a whole brain using current technology. Now we can go through it in less than a second. So you can get a full image of the brain every second. But the trade-off is the resolution is not going to be 1 millimeter, but it's pretty close. With state of the art, you can do actually 8 millimeter cube with about 800 milliseconds. Okay. So every 800 milliseconds, you can get a pretty high-res image of the brain. And the way we do that is with a sequence that looks very much like what you see in the homework, which is this echoplanar imaging sequence. Okay. So the trade-off is, instead of going TR and acquiring a line and then doing another TR and acquiring a line, We do one RF pulse, and then we just try to zigzag very quickly through K-space. So what it looks like is with fMRI, we're acquiring a bunch of images, and typically in the presence of a stimulus. It's going a little slow. Okay, so for in this case, for example, we might show a flashing checkerboard that lasts for 20 seconds, and then the off period here is 60 seconds. And while we're doing that, we're acquiring all these images. And then if we look at any sort of one voxel here, we can look at the signal go up and down, up and down, up and down. Right? And then the typical analysis, so where fMRI starts to vary a little bit from traditional MRI, where traditional MRI is primarily, the radiologist looking at the images. In fMRI, there's a lot of statistical analysis that's done. So basically, we're asking the question, which parts of the brain is the correlation between what they measure and the stimulus significant? And so, for example, this is sort of what's called an activation map, and these are showing all the voxels that are significant, where the time course of the voxel looks a lot like what the task was. Yes, question.
So if you're like in the fMRI, like
yeah,
the metal inside of the like causing problems with the MRI system.
Yeah, typically the projector is outside the room, and then we just beam it in. There are goggles that people have designed that are MR safe. They're super expensive. It's like $100,000 for MR safe goggle. Anytime you develop anything MR safe, it's like usually 5 to 10 times the cost of what it would cost to have a non-MR safe device. You don't necessarily need to remove all the metal, but you need to remove enough such that there's two things. One obviously is, if it's got a lot of metal, it's a danger, right? But if you take a circuit board, it's not got much metal on it, right? So it's really not a danger. But the problem is it may not work in the MR environment because you got all these magnetic fields and switching magnetic fields. And also you don't want any electrical signals from this to interfere and cause noise in your MR image. So the trick is, how do you keep those two electrical environments separate so they don't interact with each other? It's not too hard. I mean, we had a study a long time ago where some grad students took like a Nintendo game controller, right? Because we wanted to have them do like a virtual reality experiment in the scanner. And so they just took an off-the-shelf one, and they took it apart and then stripped out all the parts they could, and it actually worked pretty well. It wasn't easy, but it is doable. So that was like I think the reason for that is, they could buy like a $50 controller and strip it out and make it MR compatible. If you were to buy that from a vendor, they'd probably charge you $5,000. Okay, because if they're going to sell it to you, then they have to do all this sort of testing of it. Yeah. So this is sort of just a example of how sometimes the images are displayed, mostly because they look pretty cool. You can sort of create these 3D images of the brain and then sort of slice the brain virtually and then show where the activation is. In this case, they're tapping their right hand because you're seeing the activation in their left motor cortex. So what we want to do is talk a little bit about and at least give you some basic understanding of what's going on with fMRI. So remember, there is this echo time dependence. And so now we're going to we've looked at 1 over T2 prime, T2 star before, and now we are going to explicitly introduce this R2 star notation. Okay? Simply because in the field, that's what people typically will look at this for fMRI. And so now the decay, instead of T over T2 star, we're writing as minus R2 star times T, but it's still this transverse decay. Okay? And it's going to involve both random motion of the spins and static inhomogeneities. For today, we're really going to focus on these static inhomogeneities and where they are and how they're used to create the contrast for fMRI. So we go back to this picture we looked at before, where if you have spins in the presence of some inhomogeneity, then they're going to get out of phase, and there's going to be some decrease in the signal amplitude. Now, if by some mechanism you're able to increase the amount of inhomogeneity, then you can increase the dephasing, and the signal decay is going to be even faster, and that's going to decrease the MR signal even more. This basic picture is what we're going to see happens with fMRI. So the basic picture we have in bold is typically the basic observation is when the brain is active, that signal tends to go up, and then it goes down when they're not active. Now, does that always occur? Not always. Sometimes in some brain regions or some tasks, you can actually make the brain go negative, the signal go negative. But for purposes of explanation, for most cases, it does become more positive. So we can imagine in some baseline condition, the signal is decaying away with some R2 star B relaxation rate. Okay. And then during an activation state, because we know the signal has to go up, that rate must be less, right? And so the signal is not decaying away as fast. And so it's this difference in the two signals that's going to give us our contrast. Right? And so that's called the bold signal change. So we're going to take that difference, we're going to divide it by its baseline value, so we get a percent change. And so it's the signal during the active period minus the signal in the baseline divided by the baseline signal. And it turns out that that is related to delta R2 star. So that's the amount that the relaxation rate is changing, times minus TE. Okay. We expect this to be negative, right? Because going from here to here, this this relaxation rate must have gotten smaller. Okay, so this will be, we're going to assume that this is less than 0, right? So this whole thing will then be greater than 0. Okay, so that's the minus sign here. And you can sort of see here, this is sort of agreeing with what we had before. If the echo time is too short, then this term is going to be pretty small. We're not going to have much contrast, right? So we're going to make the echo time big enough such that it has good contrast. Now we can't go too far out because otherwise we're going to be in this regime here, right, where there's no signal left. Okay. And so it turns out that the right echo time, the optimal echo time, is typically around T2 star. That's the optimal TE. And we can just take the baseline value for that. Okay, so let's talk a little bit about how we create R2 star. And it turns out it depends on deoxyhemoglobin. So this was sort of the key insight that people had and sort of the remarkable insight. And so here's the picture. When you have these hemoglobin molecules, when they're in your lungs, they basically oxygen atoms attached to them, right? And that carries oxygen from your lungs into your body, and in this case, into your brain, right? And so when they're in your brain, the brain needs oxygen, so it starts taking these oxygen atoms off, right? And it exposes these iron atoms in the hemoglobin molecule. And so it goes from oxyhemoglobin to deoxyhemoglobin, all right? And there's 4 of these iron atoms in every hemoglobin molecule. So therefore, you can sort of see, oh, these are like little magnets, right? And these are going to perturb the magnetic field and cause dephasing. So these are now your static homogeneities. And the cool thing is how much you have depends on how much of the oxygen was used up. The more oxygen, the more these iron atoms are exposed, the more dephasing there will be. So now we can replace that picture we saw before with these hemoglobin molecules. So they're mostly shielded. If the iron is primarily covered up by the oxygen, then there's really not much dephasing, okay? But now if the molecules are such that the iron atoms are exposed, there's gonna be much more dephasing. Okay. So if there's some deoxyhemoglobin, there's always gonna be some deoxyhemoglobin because the brain's always using up some oxygen. There'll be some dephasing. But if there's more deoxyhemoglobin, there's going to be even more dephasing and the signal should go down. That's sort of interesting. You would expect that the harder you use the brain, the more deoxyhemoglobin there should be, right? Because the brain is really using up oxygen. You expect the signal to go down. But what people have found, and the sort of the mystery at the beginning stage of MRI, is that the signal actually goes up. Okay, so what's going on? Well, it turns out that there's this trade-off between delivery and usage, right? So yeah, the brain will be using up more oxygen. So that's the CMRO2 term, which is the cerebral metabolic rate of oxygen. And that's also related to what's called oxygen extraction fraction, which is how much oxygen you're taking out. Right? But at the same time, the brain can deliver more oxygen, right? It can increase the blood flow. Say, hey, I'm using up oxygen. I better send more oxygen there. So it turns out the amount of hemoglobin that's in your veins is this determined by this ratio, CMR2 over CBF. So the more metabolism you have, yeah, that's going to increase the hemoglobin. But you can counteract that by delivering more blood. And it turns out that, you know, through evolution, the brain has set itself up such that the percent increase in CBF outweighs or is greater than the percent increase in CMR2, typically by a factor of 2 to 1, anywhere from 2 to 1 to 3 to 1, let's say. And so CBF is going to go up much more than CMR2, so that CBF tends to make deoxyhemoglobin go down. CMR2 tends to make deoxyhemoglobin go up. And because this percent change is about 2 to 3 times this percent change, overall deoxyhemoglobin is going to go down. And basically, so the brain has basically set itself up so it's never going to lack for oxygen, which seems like a pretty good design, right? If you're going to design something, you want to make sure that there's enough supply of oxygen to keep things going, because, you know, imagine you're back in Africa, you know, you're running away from, you know, you're in the jungle or you're on the savannah and you've got to make some decisions. And the last thing you want to do is, you know, have your brain run out of oxygen and you can't decide what to do as you're running away from, you know, a lion or a tiger. Okay, so it sort of makes sense that you should probably make sure that there's enough oxygen to keep the brain going. Now, this is a sort of cute animation that one of my grad students made up a long time ago, where you're sort of seeing oxygen being delivered here, and then there's deoxyhemoglobin as the brain is using up. And so when there's neural activity, that tends to increase metabolism, and that will tend to, it turns out that if you look very closely, there actually is an initial change where there is actually more deoxyhemoglobin for just a little bit, maybe 1 or 2 seconds. And so actually people, if you look hard enough, you can actually see this initial decrease in the signal. Okay. Which sort of makes sense. It's sort of like if the sensor, basically the supply is lagging the sensing by just a little bit, you know. But very quickly, the brain's like, uh-oh, I need more oxygen. So it's actually going to increase the blood flow by quite a bit and open up the vessels. And that's going to decrease the overall amount of deoxyhemoglobin. And then now you're going to get, since there's less deoxyhemoglobin, there's less dephasing, so the MR signal goes up. And then at some point, it returns back to baseline when it doesn't need to do anything. Now, as we'll see later, the brain's always doing something. So this is more just in reference to its baseline state. Okay, so let's do a few quick, let's do maybe like 2 of these. So let's do number 2 first, okay? And I'm going to open up the poll for online so you guys can respond online. Okay, so this is fairly, you know, shouldn't take too long. So let's just, you know, maybe look at this question. So it's saying an increase in the functional CBF response will tend to either decrease or increase or decrease the bold signal. So go ahead and we'll give you about 30 seconds to respond online, just, and then we'll sort of do a quick poll in person here. Okay. And think about that for a little bit. Okay, so let's so got a pretty good response rate online. So in person, fairly just at when I say 1, 2, 3, just say increase or decrease. Okay, 1, 2, 3. Okay, so it sounds like overwhelmingly decrease, and then it's also 86% online say decrease. So I have not drawn, yes, go ahead. Question 2, right? Are we doing 2? Was everyone doing 2? Yeah, okay. So I obviously have not explained things very well because the answer is increase. Okay, so let's go through this. So if I increase this, if the CBF increases more, right, that's going to deliver more oxygen, right, and comparable to CMR2. Okay, so if there's more oxygen, there should be, if there's more oxygen delivery, there should be less deoxyhemoglobin because we're delivering more oxygen faster than it can be used up. Okay, and that will tend to increase the bold signal because there's less deoxyhemoglobin. Okay. Any questions on that? Sure. So just think about, you just need to think about sort of how much oxygen is there. Okay, so the CBF, cerebral blood flow, is delivering oxygen. So if there's a functional, if there's an increase in that response, so there's more CBF being delivered, right? Then on average, to first order, there's just gonna be more oxygen available. So, and therefore there's gonna be less deoxyhemoglobin because my supply sort of is outstripping my demand, right? And so therefore, less deoxyhemoglobin means less of those iron atoms are exposed. So there'll be less dephasing, and therefore the signal should go up even more. Okay. Okay, so I'm going to relaunch. Sorry, so let's do this question next. Number 3, an increase or decrease in the functional CMR2 response will tend to increase or decrease the bold signal. And this is sort of, and these questions are sort of saying all things being equal, like if it's really just CMR2 that's changing mostly, what will happen to the bold signal? Okay, so I'll relaunch the poll online. And take about a minute to think about this, and then we'll regroup. Okay, great. So let's do an in-class poll. So in the count of 3, just tell me whether it's increase or decrease. 1, 2, 3.
Increase.
Okay, so I hear mostly decrease here, and it's 63% decrease online. So yes, it is a decrease. All things being equal, it will tend to decrease because the more metabolism there is, the more oxygen that's being pulled off. So you're going to expose more of those iron atoms, and there's going to be therefore more dephasing, and therefore the MR signal should go down. Okay, so good job. All right. So it's been a while since I made up this slide. The purpose of this slide was, this is sort of from The Simpsons, obviously, Homer. And I think this was written in, when he drew this, he probably didn't think that all these things were studied, but it actually turns out that pretty much everything there has been studied. Specifically, I think the only thing that I couldn't find was donut fMRI. I'm not sure anyone has actually studied donuts, the effect of donuts, but there certainly has been a lot of studies of obesity and eating disorders and things like that. So I think that's sort of close enough to donuts that it would count that pretty much everything that Matt Groening said would be studied, it has been studied. Okay. Sort of one of my favorite studies is this one from Caltech, which I like it because it sort of tells us how easily we are manipulated by the marketing of things. And so the experiment here was quite interesting. Basically, people were given the same wine, okay, and then it was in containers that they couldn't tell what it was. But in some cases, for example, here they were told that it was $10, and here they were told that it was $90. and same wine, but they're asked how much they like the wine. And obviously, when you're told the wine costs $90, you like it much more. Okay. Here, they were told the wine is either $5 or $45, and once again, they like it a lot more when it costs more. Okay. So we tend to like things when we think that they're more valuable or cost more. So then what they did was they looked at what the brain was doing. And so this was the brain response, and these are in reward areas of your brain. These light up when you sort of feel like you're being rewarded. And so here you can sort of see here for the $45 wine, it's a pretty, you're pretty happy, the brain is pretty happy here, okay, saying I'm getting rewarded. And then the $5 wine, much less response. And then here there's even a negative response, okay. And similarly for the $90 wine, very positive reward response. And for the $10 wine, not so much. Okay. So this is sort of interesting. I mean, it really is showing that, you know, whatever networks are evaluating reward are very sensitive to pricing. Okay. And this is why, you know, why people would be willing to pay $4,000 for like a Louis Vuitton or a Gucci bag that costs $50 to make, right? Because it actually does provide value, you know. It may not be worth anything, but you're getting the value of feeling like it is rewarding to your brain. So I thought this was an interesting study. So yes.
Now, the pictures on the right are from like one person, or
Let me see. In general, when they do these studies, this will probably be a group average. So even the curves, I mean, there are error bars there. I've not read the study for a while, so I don't hold me to that. But in general, these fMRI studies typically involve to get something published. You can't for at least for human studies, it's very hard to get something published if it's only in one subject. It used to be you could publish with 5 or 10. Now it's like 20 or 30 subjects. Where it's a little different for monkey studies, where you can actually publish studies with 1 or 2 monkeys and just have them do lots and lots of trials, just simply because people know you can't scan tens of monkeys. Okay, so I mean, which is a little odd. I mean, there are some studies where they've scanned one, like for example, there's a very famous study where one professor had himself scan every day for like a year. So you can publish studies like that because they're just sort of so unique. And he basically tracked his caffeine usage, you know, his dietary intake, all these sorts of things to try to sort of see what was going on with his brain. Okay. Yes. You can, but it's very difficult. So there is, you can look, for example, put an EEG cap. You can do that. The problem is that when the gradients switch on and off in the scanner, they cause electric fields that interfere with the EEG. And then also your brain, maybe next week I'll show you some pictures. Your brain actually pulsates. You can't feel it, but your head's pulsating right now with every heartbeat. And that movement of the wires in the magnetic environment also is a big problem. These are bold signals. These are fMRI signals. Yeah, these are based on what we just talked about. Yeah. But yeah, you could do this with electrical, but the problem with EEG, for those of you who know about EEG, you just don't have the good source localization. Yeah. So with fMRI, the advantage of fMRI, you can tell where something is. You don't necessarily have great temporal resolution, so you're in the 1 second temporal resolution, but you know where it's coming from. With EEG, you can get very. Go ahead. Yeah, but even these electrodes have a lot of overlap, and also the problem is that if you think about it, even if you like an fMRI thing, you might be looking at 100,000 voxels, right? So that's pretty typical. Even a high density EEG cap is maybe 200 electrodes. So using 200 measurement points to estimate something that's going on in tens of thousands of brain regions. It's what's called an ill-posed problem. Yeah. So you can't, at this point, you can't get the spatial specificity. You just don't have enough data. Okay. And it's not a matter of, and the problem is you're measuring things here, right? Whereas fMRI, you're actually getting signals from in the brain. Now, in the future, that might change, right? Because, with nanotechnology and things, and whatever Elon Musk does or other companies, I mean, it's not out of the question that, 50 years from now or even sooner, people will be willing to have lots of wires injected into their brain. And you could have like a wire, every millimeter. There might even be something like done right now. I don't know. I mean, there are, in terms of treatment, there's much more willingness to put basically pacemakers for your brain, right? There are implantable electrodes now where they basically zap your brain to deal with things like epilepsy or depression. So I think if the nanotechnology, if they figure out a way to put that into the brain and deliver it in a way that doesn't destroy the brain, I think that's potentially what we'll be seeing. Another key thing, we'll just end this today with fMRI and sort of few things you can do with fMRI. This was something where this is the area called mind reading, where they're trying to take the fMRI, the data from the brain, and predict what the person is seeing. Okay, so what you see here is the presented image, and then what their prediction of the image was. And let me see if I can play that.
So this is a decoder built for primary visual cortex. On the upper left is the movie the subject saw. On the upper right is the decoded result. Primary visual cortex represents the structural elements in movies like for local edges and textures. You can see that this decoder does a fairly good job of recovering the structural information, even though we're only decoding one brain area. This is a decoder that is recovering information from higher level visual.
Anyways, there's a video link to that on the bottom, so you can look at that. So it's not quite perfect yet, but I mean, it is a sort of proof of concept. How useful this is, I'm not sure, but it's sort of saying that there is enough information in the brain readings, at least to come up with some very, at least rough estimates of what the person is seeing. One potential application of this is, for example, if you had someone who couldn't respond, like in a coma, or and you want to see what their brain was doing, whether they're dreaming or not, then this would be an interesting application of that. Okay. I mean, they've done studies where, for example, if you tell someone who's sort of can't respond, but tell them to imagine someone playing tennis in their brain, then actually they can get a response for things like that. Okay. Another area is called real-time fMRI, which is sort of interesting, which is basically like if I tell all of you right now, go ahead and deactivate or increase the MR signal, increase your blood oxygenation in your precuneus, then most of you would be like, well, I don't even know what the precuneus is. I don't know where it is. How am I going to do that? Or I might say, increase the blood in your amygdala. That might be a little easier. If you imagine something scary, you would increase the blood flow into your amygdala. Okay. But another way you can do it is if you just show someone their MR signal, you can sort of place your cursor on some part of the brain and then display and measure the MR signal in that part of the brain in real time, and then display that up, down, give them an indication of whether it's going up or down. Then you can actually train their brain to go up or down. Okay, because the brain, as you all that's how we learn most things. You just get feedback, and like when you ride a bike, you sort of figure it out. The same way, if I just show you whether things are, whether you're making something go up or down, it's pretty remarkable. You can actually train someone's brain to make any part of their brain go up or down in terms of the MRI signal. Now, whether they can do that afterwards, seems like it's not the case. But given the feedback, it does seem like the brain can do that. And the last thing I want to talk about is, so far we've really talked about what's called task-related fMRI, which is sort of the response to an explicit task. But a big area of the brain now is just putting people in the scanner and measuring the brain as they're essentially doing nothing. And even though you're doing nothing, you just imagine you're just lying in bed. Clearly, a brain is not doing nothing. It's still doing a lot. Doing a lot of housekeeping. You're having wandering thoughts. And so the idea is that if you just look at the brain and call it in its resting state, it can give you a lot of information. In particular, if you have someone tap their fingers in the brain, these areas of the brain will light up. But if you just let them rest in the brain and say, what does an area in the left motor cortex look like? Maybe that's the red the blue signal. And then if you look over on the right cortex, that's the green signal. And it turns out areas of the brain that act together while they're doing a task are also highly correlated even in the resting state. And so what this has allowed us to do is create these really nice maps of how the brain is functionally organized, essentially looking at the connectivity, what's called the functional connectivity of the brain. And this is now the basis of many, many large scale studies that are being done with tens of thousands of subjects, just using that to sort of see how the brain is connected essentially between different brain regions. Okay, and then whether those connections vary with disease or age or other conditions. Okay, so we've reached the end of our hour. So I'll stick around if there's any questions. Otherwise, have a great Thanksgiving holiday, and we'll see you next Monday then.